So let's get started, right? So what we discussed like just now is that like we proved the first step, if you remember, right? I mean, this thing we actually proved. Step 1 we actually proved. Step 2, it's not very bad. If you trust your physics knowledge, I did not, right? I mean, and clearly Piyush does, right? So this step you should sort of believe. I mean, I did not do it to my satisfaction, so I will put maybe like not a very confident question mark, okay, right? Because I did not do it to my satisfaction, and now we have to like do this step. It's the third step, which asserts that this quantity, the desirability value of an edge E, is actually like somehow mysteriously, right? It exactly equals the maximum fraction of energy over all choices of potentials that the edge E consumes as a fraction of the total energy dissipated across the entire circuit, right? So that's kind of okay, remarkable, but okay, like it's not such a bad proof. So let's prove this. So notice that the image of the Laplacian, right, is the space orthogonal to all ones, 1 perp, right? This is also equal to the image of the Laplacian pseudo inverse, and I'm like looking at only x's coming from 1 perp in the right hand side over here. The right hand side only examines x's living in 1 perp. Okay, so that's good. So here is what I'm going to do, right? I mean, proof of the claim asserted in the third step, right? So like let's see. Notice maybe I used a big word like so L dagger. So like what is L dagger? So let's make sure we know what L dagger is. And L is summation lambda I ui transpose. Lambda I not equal to 0. Lambda I not equal. Oh yeah. The graph is connected. Sorry. Yeah. Okay. I'm talking about spanning trees. I want the graphs to be connected. नहीं तो spanning trees कह रहे हैं बातें क्यों कर रहे हैं? Right. Yeah. Okay. So like let's consider the map that takes x to L dagger x. Okay. And the idea is that I'm trying to maximize over x's living in 1 perp of the right hand side, which is x transpose Lex over x transpose Lx. Right? Of course, you should notice that if x was parallel to all ones, right? I mean, we are looking at 0 by 0. So this quantity is exactly equal to max over all y in 1 perp. Right? Just like variable renaming, substitution, whatever you call it, y transpose L dagger. Okay. Le I will write it in a different color. Le, okay, L dagger y divided by what I get over x transpose Lx. Okay, yeah. So this becomes y transpose L dagger. I'll write L in that color. Oh, when like this is the all ones vector. All ones vector. It's all ones, right? Ly. So that's fine. And like you notice, this term drops off. L dagger bhi tha ek. L dagger. Okay, great. Right, so this is the expression that I'm looking at. So I hope you agree that this is an equality, like should be apparent. Max over all y in 1 perp. What I will do, this was perhaps not the black pen I was using, maybe I will using this. Yeah. So y transpose L dagger. I'll write this thing Le as Be transpose, right, times L dagger y divided by y transpose L dagger y. That's equal to max over all y in 1 perp of what? So like I'm looking at y transpose L dagger BE, BE transpose L dagger Y. That's just the two norm of this scalar. This quantity is a scalar, right? Y transpose L dagger BE square over y transpose L dagger Y. ओके ठीक है. L dagger एक PhD मैट्रिक्स है. PhD मैट्रिक्स का अपने स्क्वायर रूट ले सकते हैं, राइट? वी कैन राइट L dagger as M transpose M. So this is equal to max over y in one perp. ये लिखते लिखते थक रहा हूं. Yeah, it's PhD, right? It's PhD. It's PhD. So max over all y in one perp of y transpose M transpose M BE square divided by y transpose M transpose MY, also known as MY का टू नॉर्म स्क्वायर. अब यहाँ पे कोशिश वर्ड्स लगाते हैं, ठीक है? तो A डॉट B इज लेस देन इक्वल टू A का टू नॉर्म टाइम्स B का टू नॉर्म. ऊपर स्क्वायर भी बैठा हुआ है, तो दिस बिकम्स मैक्स लेस देन इक्वल टू, राइट, MY टू नॉर्म स्क्वायर टाइम्स MBE टू नॉर्म स्क्वायर. गुड. चीजें कटती तो अच्छा लगता है, राइट? ओके. दिस क्वांटिटी is exactly equal to max over y in one perp of what? So like this is like also known as BE transpose M transpose MBE, which is the same as BE transpose L dagger BE, right? और ठीक है, right? तो also equal to max over y in one perp. So I'm like these two equalities, these two things are what you would like to look at. Something making you unhappy, Raghuvansh?
So that last line in the second column.
Last line.
Yeah, there's a. This is probably a stupid question. What happened to the B transpose?
तो B transpose L dagger Y और ये दोनों चीजें they are transposers of each other. These are transposers of each other. ठीक. उसके बाद कुछ नहीं किया. L dagger को मैंने M transpose M लिख दिया, ठीक है, और कुछ कैंसिलेशन मिल जाता है, बट आपको लेस देन इक्वल टू आ जाता है, राइट? So what we have discovered is that like this max, whatever expression I had, like it's less than equal to like this thing, BE transpose L dagger B. That's the like expression that I had over here. So I have discovered that this max value is less than equal to. So like maybe let me just put this here more prominently, right? It's less than equal to max over like all y of like this expression. I'd like to tell you that like okay. So why this does not depend on y. This does not depend on y. Yeah. So that's what I was trying to like get at, right? Okay. Okay. Yeah. Sure. This does not even depend on y, right?
And then we can put y equal to B.
You can put so that's the next question I was going to ask. I was about to ask like what Mehul just answered. You can show that this inequality is in fact an equality. Plug in y equals B.
B is equal to 1, right?
Yes. B is minus 1 and 1.
Yeah, so, yeah.
Thank you. That's important. Okay. Good. Great. ठीक है. तो this is like an interpretation of like this quantity's desirability value in terms of like this energy dissipated like across the circuit that many people like. We did not have to do that, right? I mean, yes.
If time is left in the end, would you revisit step 2?
ठीक है. Like we'll do that later, okay? During the lunch hour, during the lunch time, okay? Good. तो हमने क्या ऑब्जर्व किया? Like we have been able to express the desirability value as this quadratic form. right, which as the ratio of these quadratic forms that people like, this energy distribution view. This thing is given a name. I mean, people call it the effective resistance, right? And like we already mentioned that name in part 1 earlier. Okay, so what we want to do now is want to sparsify a graph. Of course, you want to preserve something, right? अगर specify करना है सारे edges फेंक दो, right? Yeah. So we want to meet some goals. So let's see what goals you would want to meet, and you will see a more advanced version of whatever discussion I am going to hand wave over, because I'm going to hand wave brutally, and then after this hand waving, of course I will do a more detailed treatment later in the class when we continue. Right, so there are really two directions here, and I want to talk a little bit about both. That's why I have to hand wave, and I will hand wave both. So the first direction is we talk about graph sparsification, and the second direction is talking about a faster algorithm than the one that we have seen for generating uniformly random spanning trees. So there are these two directions, and we would try to tackle both of them in a hand wavy fashion. So let's see what's the goal in sparsification. First, we would state the goal that normal people would try to think about. So the idea is that you are given some epsilon, right? And what you want is for n large, given algorithm which on input a graph G equals VEW. W is a positive weight function on the edges, right? So W is the weight function on the edges. I will not write that. What you would like to do is this algorithm should return given algo which returns a graph H on the same vertex set with some different edge set and some different weight function, such that with high probability for all cuts, ठीक है? तो मेरे पास कोई कट है ग्राफ में, तो let's क्या LI UST, sorry मेरे राइटिंग खराब है, yeah. So you have S complement, इसके बीच में कुछ edges जा रही है, edges का कुछ total weight होगा, right? The total weight is weight of this guy plus weight of this guy plus weight of this guy, right? So WGSS complement is just equal to sum with respect to the weight function on the graph G, right, where the edges belong to this cut. Right? So that's the weight. So what I would like to do is that for every single cut specified by this subset capital S of vertices, I would like that the weight that you return is actually pretty close to the original weight. The weight that you return one plus epsilon times. So what this is saying is ki this is asking the following ambitious question. I give a graph G. Of course, one thing that I did not emphasize is that I want EH to be a subset of EG. Right? So I give you this graph G. It has loads and loads of edges. Right? And of course, I would want EH to be much smaller. So that's a part that, so maybe I want to give myself more space. The first condition is for all subsets of vertices, you would want and the second thing that you would want is that the size of EH is small. Right, so you are given this graph. What you would like to do is you would like to tear it down. It has too many edges. You want to end up with a graph with significantly fewer edges. Okay. Now, what is this significantly fewer? How few can we make it, right? How small a graph can I end up with so that all cuts, their weights are essentially preserved up to like this 1 plus minus epsilon, right? Okay. So think of epsilon as like being sufficiently small, like 0.01. तो मतलब जो भी weight मैं return कर रहा हूँ, it's like between 0.99 of the original weight and 1.01 times the original weight. That's the goal I would like to achieve. Okay. So, like people who resolved this challenge, they are called Benzer and Karger. And like Karger earlier had a single author paper back in 1996 where he tried to approach this goal. I'm going to like super briefly like scratch like what Karger did. Even scratch is perhaps a wrong word. So the solution template was pioneered by Karger. The solution template is something like this, that for every single edge, what Karger would do is that he would toss a coin with probability of heads equal to PE. Okay. I have not told you what PE is. I'll just tell you that PE is chosen suitably. Okay. That's the only thing I'm going to say about it. Right. So, like what you are going to do is that you are going to toss these coins attached with an edge E, right? And you toss coins across all the edges. Right, so at the end of this day, you will obtain a graph H, right? You will obtain a graph capital H, which corresponds to all those edges which tossed heads. So the graph that you obtain is going to be a random graph. So obtain a random graph capital H, where E sub H is precisely like corresponding to all those edges which tossed heads. Okay, right. So what Karger does is that he sets the weight of the edge to be 1 over the probability PE times the weight in G, right, with probability PE, and he sets it to be 0 otherwise. Why is Karger doing this? Because what Karger would like to have is that in expectation, right, the weight of an edge is preserved. So notice that the expected weight of the edge E is going to be PE times 1 over PE times WGE plus 0, right, which is exactly equal to WGE. So Karger wants to preserve like all edges, the weights of all edges, and then he shows by a very clever argument that like if your cut is small, okay, you can't have too many small cuts. So like remember, I mean the thought template that you have in your head is something like this, that there are big events and there are small events. So big events would be something like you want to like handle cuts of large size. You can have many cuts of large size, but then concentration bounds are precisely going to help you out with this situation. That so like for now, let's even talk about undirected graphs. Okay, all weights are 1. Let's say all weights are 1. Okay, really in the like large weight case, you talk about cuts with large weight. But like let's talk about undirected graphs for a minute to get better intuition. So the idea is that like we are talking about like cuts that are crossed by like that have large total weight. So like such cuts you can have many, but such cuts are also easier to hit by random sampling. Okay. Of course, the annoyance comes when you want to bound the probability of a bad event, of a tail event, which corresponds to small cuts. But then Karger shows that you can't have too many small cuts. Okay. So like a similar union bounding trick would allow you to navigate those situations. Okay, so, but like that's really the only thing that I want to tell you about Karger, right? The thing that I want to inherit from Karger is solution template, and I want to consider a different problem. The argument is probabilistic. In fact, I will prove this in the class. right? But like for today, I want to like just give you a like sense of like what's going to come, and like for those of you who miss this class, the recording will be available, but I would also go over the relevant pieces of the lecture when they come.
The missing thing is definitely the choice.
Yes, the missing thing is choice of P. Yes. So actually, I just write a statement, again a vague statement. So if you sample edges independently with well chosen coin probabilities, whatever that means, well chosen coin probabilities, such that it satisfies that the expected number of edges in H is theta n log n over epsilon square and log square n actually. So of course I'm going to assume that the source graph G had at least these many edges. If the source graph G had fewer edges than this, तो हम बात ही क्या कर रहे हैं, right? Like I can just return the bloody graph. So I want to tear the number of edges down to a manageable number, and by EH small I meant precisely that bound. Okay. So my graph had at least n log square n over epsilon square edges. So Kargar says that if H satisfies this with well chosen probabilities, what you would have is the condition of the theorem would be met. For all subsets of vertices, you would in fact have that WHSS complement lies between that's what Kargar showed, right? So there are going to be like very few proofs in this part of the discussion. Like the only thing that I guess I will mention is so first I will introduce the other problem, and the only thing I will mention is that the coin probabilities that we have introduced, this X transpose LEX over X transpose LX. So that's the like only thing that yes.
We let the PE be the probability that the edge is included in random spanning tree. That seems like a
Better choice.
huh,
Yeah, I agree. You are absolutely correct. So that's what is going to come up next. Okay, right? Yeah. Okay. So absolutely correct. Okay. So like for those of you who did not hear Mehul well, right? What Mehul is pointing out is that there is an obvious choice for PE that Mehul can think of, right? So Mehul can make this vague statement, not vague, by saying that like let's choose PE to be exactly equal to the effective resistance, right? Proportional to the effective resistance. That's precisely what we will do, and we will end up with an even better primitive. So I'm going to invent for you a primitive that is superior to the Kargar primitive. What Kargar can do is कि Kargar can preserve all cuts. अच्छा तो क्या edges बचाएगा, मैं उससे ज़्यादा बचाएगा, right? So that's the spirit that we will have in this discussion. So the idea is that like with cut specifiers there is this annoyance. I have built a cut specifier. Okay, I claim that I have built it. Now can you verify it? Looks like a very painful task. I have to go and verify for every single cut whether that cut was preserved to 1 plus minus epsilon. It's a very tiring thing, right? In fact, it's NP hard. Okay, like I mean, we do not know of good algorithms that can avoid brute force, right? If given a graph H, which is claimed to be a sparsifier of like a graph G, epsilon sparsifier, 1 plus minus epsilon sparsifier, verifying whether it is legit cut sparsifier is not easy. This primitive is called a cut sparsifier. So I should have given you that name. What Spielman and Shrivastava came up with, okay, like towards like they were studying a like fairly bizarre goal. I mean, even the goal sounds bizarre to me. Like maybe Piyush will disagree. So the idea is that you are given a linear system, Laplacian linear system. So you want to solve Lx equals B. L is a Laplacian. But like unlike normal people, you want to solve it super fast. You want to solve it in nearly linear time. So what Kargar suggested, what Spielman and Srivastava suggested is that it might be better to pass on to a different linear system corresponding to a sparser graph. So maybe I can invent for you a sparse graph capital H, and I can try solving LH times x equals b, and maybe I can solve that faster because H is sparser, so LH will have fewer like non-zero entries. Most of the entries in LH will be 0, and maybe this linear system I can solve fast. And in fact, Kargar like made that dream come true. I'm saying Kargar, I'm sorry, Spielman made the dream come true. And the entire idea here is that like towards this journey, he introduced a different primitive. I'm going to introduce that primitive. Solution changes by a little. Solution does change by a little, but like you can find epsilon accurate solutions fairly rapidly. So Spielman's Srivastava, I should say, primitive. So they want a different primitive. They have a different goal. They are also going to think of a sparsification problem, but their sparsification problem is much more bolder. They are trying to sparsify not just cuts, but many more things. Yes.
That's one question. How much is this graph classification related to trying to embed the graph into a lower dimension?
I don't think it is.
Because you are getting similar boundaries, let's say.
I mean, like a 1 over epsilon square is like prototypical thing that shows up almost everywhere. Log n over epsilon square, it shows up everywhere. Do you have a better answer, Piyush? That is this connected to?
One of the first is sampling.
Yeah.
Both of these. But we are geometry is not.
Yeah, I mean, I would imagine also not. At least none that I know of. Okay, so what? Nikhil Shrivas is this? Yeah, but like the two are close buddies. Piyush and you, Piyush and Nikhil, right? Nikhil Shrivastava. But I mean, I invited him at like IIT Bombay for a lecture, and like what happened is that like in that lecture he did not talk to anyone at IIT Bombay, but he talked to Piyush. Yeah, he did not even talk to me. Okay, this is all recorded. I'll send it to Nikhil. Okay. Oh, all right. So, what is the primitive that? Yeah. So, what is the primitive that Spielman and Shrivastava were trying to build? This is called a spectral sparsifier. Spectral sparsifier. And as you will see, like there is a very nice thing that they built a object, spectral sparsifier, which implies cut sparsifiers. But lo and behold, we are in this very weird situation that whatever this object is, I will define it in a minute, right? Verifying it is easy. So I claim that I built a spectral sparsifier. Okay. I challenge you to verify it, and you can say, "Oh, yeah, I know how to verify it." So let's see. How to verify it? I'll ask it as a question to the class. So like what the primitive is, let's see. So again, I fix some positive epsilon for n large. Right. This graph is a graph on n vertices that I forgot to write. For n large, give an algorithm which on input a graph G with n vertices and like m edges, m being like really large. And then n to the like 1.1. Right. What happens is that this algorithm should return a graph H such that what you have now is that for all real valued vectors, x transpose LHX lies between, I will write it directly, lies in 1 plus minus epsilon x transpose LGX. And the number of edges in H is better than what you get over here by a log factor. So that's the primitive that Spielman and Shrivastava built for us. It's a beautiful result. I claim that this primitive implies that primitive. Why? अगर आपके पास स्पेक्ट्रल स्पर्सिफायर और कट स्पर्सिफायर फ्री में मिल जाएगा, क्यों? Frame each cut as an x, right? How will you do that?
Like you can choose up to a negative factor 1 and
I mean, just choose x equal to 1 sub s. So given a set capital S of vertices, choose x to be the indicator vector for the set capital S, right? So indicator vectors का quadratic form आप compute करोगे, that's precisely the cut size, right? So this thing captures that thing. The number of edges that Spielman and Shrivastava got was better than what Kargar got. And now answer the following question. I claim I have built an epsilon spectral sparsifier. Okay. Challenge, verify this. Okay. You can't verify it for uncountably many vectors, but I am claiming that this can be done in polynomial time. How?
You only need to look at your eigenvectors and some eigenbases.
Yeah. You only need to do an eigenvalue computation, right? I mean, yeah. Okay.
Like, what is the complexity of the convergence?
Complexity of this computation. The running time, you mean?
Complexity of computing LH.
Oh, complexity of computing LH. So, I mean, everything Spielman and Shrivastava are able to do in linear time. So, this is the running time, right? I mean, nearly linear time. So, that's what, so we call this nearly linear, okay? I mean, there are these words that people throw around, nearly linear, almost linear, and I forget which is which.
Number of edges, but like the complexity of construction of edge.
Yeah. So, you can output H in time proportional to the size of each. You can output H in time proportional to the size of each. So that's pretty remarkable, like these people achieved this, and we have discussed a few remarks like that. I will just write to make sure that, like, you know, we are on board with like what we just discussed. So the remark is that epsilon spectral sparsifiers imply epsilon cut sparsifiers. Sorry, what? Running, it does not. So what Kargar is able to do, Spielman and Shrivastava are able to do. So like perhaps this is a question that Piyush can answer better than I can. The running time of the algorithm that Spielman and Shrivastava pioneered, that is nearly linear, right? That is nearly linear because, sorry? They have to solve the effective resistance, but I mean like what they are able to do is that I mean their grand goal is to solve a linear system fast, and they go via this route of computing LH, right? So it has to run in linear. There are lots of other tricks. I do not really understand what's going on. It's a pretty like impressive feat that somebody achieved this. I do not know like how they avoid like reading the entire input. I do not know this.
No, I think the way this classifier thing is just you don't. I mean, so see, even if it took a long time, it's still a valid primitive for linear equation solving because you can then solve it for several weeks.
For several, so you're saying that I amortize. I amortize.
Yeah, no, as in like in many applications, the way the source is changing. The right hand side is changing, but the matrix remains the same. So your system, circuit is fixed, but you're already where
Oh, I see what you're saying.
So
I don't worry about the time to compute LH. Yes, the pre-processing time I don't worry about. Okay, yes, then the running time can be more. Then the running time can be more and should be more. Okay, fair enough. So Mehul, my answer to you was incorrect. Okay, the answer, the running time can't be proportional to the phase. Me too. Like I did not have an answer for this. The only thing that I knew was the punchline that it's a nearly linear time solver. So I assume this step must be doable in linear time as well. Okay, but then clearly like. So let's verify that later. For now, I will say what I'm more comfortable with, that I do not know how to compute EH in time. I do not know how to compute H in time proportional only to size of EH. Okay, so let me still make those remarks that I was saying. Right, the other remark is that like you know, you can verify whether a graph H is an epsilon spectral sparsifier for G. So now I want to like switch gears and talk about another thing that Mehul pointed out, that we are going to use the same solution template to obtain an epsilon spectral specifier. The template is that I'm going to like attach to all edges these sampling probabilities vis-a-vis. I'm going to obtain a random graph capital H, and I'm going to like say that hey, looks like job done. I have like an expectation, preserve the weights of every single edge, and maybe that's it. For well chosen coin probabilities, the coin probabilities will be chosen precisely to be the effective resistance values. So, for instance, like what I'm saying is, maybe I should write it in a different color, that choose PE to be equal to X transpose LEX over X transpose LHX, the max value that this thing takes, I'm sorry. Right, choose PE to be like exactly these values, and what you would discover at the end of the day is that the expected number of edges that I'm sorry, that for a fixed vector, okay, right. So so what you will have is that so let X denote like the sum of XE's, where XE is supposed to be like that expression 1 over PE times WGE, right? I'm sorry, times BE transposed, I think. Okay, so what I'm doing is that I am grabbing a bunch of PSD matrices, right? And I should be a little bit more careful. I am being very sloppy here. I want to erase that then. So that's the choice that I make. What you would discover is that like in expectation, the contribution to LH from the edge E is the contribution to, I'm saying that in expectation, the expected value of XE is precisely LE, is precisely BE transpose. So in expectation, picking the right contributions, right? And now what Spielman and Srivastava say is like a very analogous version of this statement. So that analogous version, what does it assert? Right, I mean, okay, yeah. Right, so that analogous version says that like if the expected number of edges is precisely this, yeah, I mean it's just this. Then for every x in Rn, you have X transpose LHX, in fact lies between 1 plus minus epsilon X transpose LGX. This is like all I will say on this matter for today. Piyush will continue like telling you significantly more about this in like his lecture. What I want to do now, yes, sorry.
So where is this epsilon parameter coming from? If I'm choosing the edges with like their, let's say, effective resistance, how am I using this epsilon parameter? That is completely deterministic, right?
No, so that comes from you want to get your concentration bounds to work out. You want to get your concentration bounds to work out.
No, I'm saying the number of edges.
Yeah,
Number of edges.
No, so like the response is something like this. That look, in expectation, what you would have in expectation, the graph that you output, it's called capital X. Capital X is summation XE. So the expectation of X will be exactly equal to LG. So in expectation, I'm doing the right thing, but I want to get a high probability version of it. In order to get a high probability version, the dependence on epsilons will emerge.
No, that's not right. I'm saying the dependence of the number of edges in H2 epsilon, because the number of edges I'm having.
Okay, fine. So let's have that like discussion. So the idea is so I claim the following, that if you add all the desirability values, so maybe I'll write it over here. So Aditya, I think the better thing to do, in fact, would be, because like I have only 15 minutes, the better thing to do would be to take your question later, because like we will anyway continue this discussion throughout like the rest of the semester, right? No, no. You need better concentration bonds. It's a matrix concentration analysis. Okay, like we'll go there like when the time comes. But for now, what I will do is that I will tell you in 15 minutes, I'll try to cover L dash broader. Piyush, what do you think? L dash broader. Okay, I'll try. So I'm trying to give you an algorithm. So guys, pay attention. I'm trying to give an algorithm. What it does is that it returns a uniformly random spanning tree. Okay. So there is like major pieces that I will not be able to cover, but like that's fine. L dash broader. This is an algorithm to compute a random spanning tree. To sample a uniformly at random spanning tree. Okay, so here is the first step.
Tries to make sure anyone else except him.
Yeah. So this I learned from Piyush. The L dash broader, the Aldous, the namesake of this algorithm, the person who actually gave this algorithm, made such a huge effort of like citing like who did what, that he credits everybody else in this universe for inventing this algorithm except him. So like what?
Was he scared that this is like not gonna work out? No. Just, I think he was saying that people had talked there about him, but he was giving I think with genius analysis.
Yeah. So the idea is that you pick a start vertex in your graph. You pick the start vertex uniformly at random, and now I'm going to use like notations from the Markovian literature. You run a Markov process. तो ये यहाँ पे चल के आ रहा है, तो x1 is a uniformly random neighbor of x0, right? I mean this is the standard random walk steps कि आपने x vertex से चालू किया और उसके बाद उसके random neighbors पे हम jump करते जा रहे हैं. Pi is the stationary distribution. Pi is the stationary distribution, right? And you run this process till the cover time. So tau is the cover time. That's the first time at which you have seen all the vertices. It's the minimum over t in n, such that like you know all vertices are visited by time t, or maybe like x1 to xt. This multi-set, or this like viewed as a set without repetitions, is exactly equal to all the vertices. So first time at which you see all the vertices, right? Cover time is n square. For an n vertex graph, the cover time is n square, at most n square. So now the idea is that what we were going to return is that we are going to return a directed tree. We are not going to return like undirected tree, we are going to return a directed tree. Right? Return the following directed tree. Like this was perhaps the topic that I like more than graph sparsification. This is super cool for me. But then like I had to tell you a little bit about graph sparsification so that you are not completely lost when Professor Piyush begins his lecture. So return the following directed tree. So this directed tree is denoted AB of like this process, capital X, that's capital X. So what is like the tree structure looking like? So it looks like, you know, मैं X tau v पे जा रहा हूँ, तो I have to tell you what tau v is. Tau v is the first time you visit the vertex v. So tau v is the first time the vertex, some vertex is hit, right? और मैं क्या करता हूँ कि I arrive at an edge, I direct it in the reverse direction. So the idea is कि process मेरा x0 से चालू होता है. The process keeps going forward. मैं एक नए vertex को visit किया, एक नए vertex को visit किया. Keep going a bunch of places. The process kind of looks maybe like that. I don't know. Okay, so this is what that process kind of looks like. Sorry? हाँ, तो कवर टाइम फिनिश हो गया, ठीक है. तो अब देखते हैं क्या होता है. तो अपने इस वर्टेक्स पे पहली बार गए, ठीक है. तो ये एज इस डायरेक्शन में, मैंने मतलब ये एरो इस डायरेक्शन में डाला, ये एरो इस डायरेक्शन में डाला, इस डायरेक्शन में ये वर्टेक्स दिखा मेरे को, ये वर्टेक्स दिखा, बट ये वर्टेक्स पहले ही दिख चुका था. ओके, तो आई कंटिन्यू. Right, so this is what this process looks like. Okay, so this is the kind of trees that I'll be returning. Okay, अब ये लोग क्या कहते हैं, right? I mean the claim that I'd like to make is that ABX, ये जो tree return कर रहा है, the tree is in fact random. Okay, the returned tree comes from a distribution. What distribution? Okay, so ABX returns a random directed tree so say the returned tree comes from a distribution mu AB. Okay, what we have is that mu AB, तो mu AB returns directed trees, contains directed trees. Directed tree को हम specify कैसे कर सकते हैं? Tell me the undirected version of it and tell me the root. Right? It uniquely pinpoints a directed tree. ठीक है? तो mu AB of an undirected tree T with root V. Okay? What is the probability mass that mu AB puts on this guy? Well, lo and behold, this mass is exactly equal to the stationary mass of the vertex V divided by the number of spanning trees of your graph. So maybe इसको लोग fancy T करके लिखते हैं, right? Something like that, right? So this denotes the total number of spanning trees of your graph. Okay? The one that you counted using the Kirchhoff matrix tree theorem. So this is a claim. Okay? For now, we are going to take this claim as being true, and like we will see what we can do.
Given x size, it is repeated, right?
Given all the x size, given all the randomness here, I mean ठीक है, randomized algorithm का सारा randomness सबको पता है, तो it becomes deterministic, sure. But like there is a nice thing that is going to fall out of like such considerations. So like let's see, right? So here is the proof plan, right? So the proof plan is that this distribution mu AB, so mu AB, I'm claiming it kind of looks like pi the stationary distribution cross the uniform distribution on all spanning trees, also called UST. So the proof that I am presenting, by the way, is due to Tom Hutchcroft, and like apparently according to some rumors, like Tom Hutchcroft is one of the candidates for Fields Medal this year, right? I do not know. Okay, so the proof is like two steps. So step one kind of corresponds to that claim that I don't think I have time to talk about. So, but I'll like, so what we'll do is that we'll build a Markov chain. We'll build a new Markov chain on what? The Markov chain on the space of oriented trees. On the space of oriented trees, of directed trees. I shall write directed because of directed trees, right? Such that it has a unique stationary distribution. Its unique stationary distribution the stationary distribution will be unique by design, okay, equals pi cross UST. Okay, and now comes step 2. ठीक है, अगर step 1 हो गया, उसके बाद step 2 क्या दिखाता है? Step 2 दिखाता है basically that mu AB is exactly equal to stationary distribution of the above chain. So here is what I am going to do, right? I am required to tell you कम से कम कि कौन सा मार्कोव चेन मैं बिल्ड कर रहा हूं, भले एक क्लेम में नहीं दिखा पाऊं कि इसका यूनिक स्टेशनरी डिस्ट्रीब्यूशन पाई क्रॉस यूएसटी है, वो भले ही मैं नहीं दिखा पाऊं. आई हैव टू टेल यू मार्कोव चेन क्या कर रही है. ओके, तो मार्कोव चेन क्या करती है? इट्स वेरी सिंपल. तो यू लुक एट द फर्स्ट ओरिएंटेड ट्री दैट आई एम गोइंग टू कॉल T0. तो T0 इज योर यूनिक, आई एम सॉरी, T0 इज योर स्टार्टिंग ट्री. Like I think I have a picture for T0 that I like. Huh, I like this picture because I made it. So yeah, I'm not going to like detail it a whole lot. ठीक है, ये हमारा मतलब ट्री है T0, इसका कोई रूट है, रूट x0 है. अब मैं क्या करता हूं, right? I mean, I sampled x0. So what is happening is that I sampled x0 and then I ran this process till cover time. I obtained the first tree and that tree is written out here. Again, from the sampled x0, I also ran a different random walk. Okay, that different random walk hits like some vertex x1 at the next step. So condition on x0, like I mean the two runs are like independent. Right, so what I have is that on this separate run, I have some x1 which will have some path to this guy. x1 of course has some edges coming in. अब मैं क्या करता हूँ कि x0 से x1 पे मैं पहुंच गया, मैंने नया रैंडम वॉक किया था जो कि x0 से x1 पे गया. ठीक है, तो मैं x0 से x1 पे जा रहा हूँ, इस एज को मैं इंक्लूड करना चाहता हूँ अपने नए स्पैनिंग ट्री में. भैया किसी एज को फेंकना पड़ेगा, राइट? किसी एज को फेंकना पड़ेगा, कौन सी एज फेंकें, राइट? तो द आइडिया इज कि देयर इज अ यूनिक आउटेज फ्रॉम x1, लेट्स थ्रो दैट गाय अवे. देयर इज अ यूनिक आउटेज फ्रॉम x1, लेट्स थ्रो दैट गाय अवे. तो हमने ये आउटेज फेंक दिया, राइट? And this is the new spanning tree that I end up with, and the tree T1 is rooted at x1. Okay, right? So this is the process that I'm running. So this is the Markov chain on the space of these oriented trees. I'm going to assume that this Markov chain has a stationary distribution which is exactly pi cross UST. I assume that, right? हाँ, तो Markov chain क्या कर रहा है, right? तो मेरे पास एक ट्री था T0, ठीक है? T0 में मेरे को पता है कि हर वर्टेक्स से मतलब एक यूनिक आउटेज निकल रहा है. Each vertex is a unique outage, except for the root, right? अब x1 से भी एक यूनिक आउटेज था, right? मैं ये ब्लू एज ऐड करना चाहता हूं, तो ब्लू एज ने उसको ग्रीन बोल देता हूं. तो आई वांट टू ऐड दिस ग्रीन एज. हाँ, तो राइट, आई मीन तो x0 से मैंने पहले तो एक प्रोसेस चला करके ब्लैक ट्री ऑब्टेन किया. x0 से ही, x0 दैट इज सैंपल्ड फ्रॉम स्टेशनरी, उससे मैं दूसरा मार्कोव चेन चलाता हूं. उसका पहला ट्रांजिशन x1 पे होता है, मे बी आई शुड यूज डिफरेंट नेम y1 और x1 प्राइम. तो उससे x1 प्राइम पे मान लो मैं पहुंच गया. तो व्हाट आई एम डूइंग is that I am adding this edge x0 x1 prime. I am calling it x0 x1 only. Right? I am adding this edge, green edge, to my tree, but like it's no longer a tree because now I have a directed cycle. So what I do to get rid of this cycle is throw the blue edge away, right? And that's the new tree that I end up with. So I will have a bunch of trees: T0 rooted at x0, T0 rooted at x0, T1 rooted at x1, T2 rooted at x2, on and on and on. So this is the like process that we are looking at. That's great. So now notice that mu AB ये जो distribution है, right? I mean this distribution was invented by looking at this entire sequence. Yes.
So just to confirm, the transition from T0 comma x0 to let's call it T2 comma x1 is probabilistic. The transition itself, like.
So this new edge that I added, this new edge was like chosen by going to a random neighbor of x0. So I chose a random neighbor of x0 with the correct probability. The probability is 1 over the degree. I'm sorry, I did not get your question.
So therefore,
ठीक है, तो like another way to describe this is कि पहले मैंने एक चेन चलाया x0 से x tau टाइम तक, और इस चेन से मैंने एक random spanning tree extract किया using the Aldous-Broder spanning the algorithm. I extracted a directed tree from it. अब x0 से मैं दूसरा चेन भी चला रहा हूँ. This chain kind of looks like that. x0 से maybe I will call it y1, y2, y3, y4, right? So I'm running a new Markov chain and I will call this y1. ठीक है, that's y1. तो x0 y1 को मैं ट्री में ऐड करना चाहता हूं, तो y1 से जो एज निकल रहा था उसको फेंकना पड़ेगा. That's all I did. Right? तो मैं ये बोल रहा हूं कि mu AB क्या करता है? mu AB looks at the entire window till the cover time. ठीक है, और पूरे विंडो को देखने के बाद, right, like if tau is truly the cover time, it returns some object. Right? It returns some object. Now I claim that this thing, like whatever this distribution is, right? I mean mu AB, like at the end of the day, it's a distribution. Distribution is a key value pair, right? I mean distribution में like आपका like value हो जाएगा maybe like you know this directed tree I am looking at, and value हो जाएगा the probability of the directed tree. This distribution is exactly equal to mu AB, like followed by like I mean I don't know like I had like this tree, so store like maybe I should say like y1. Okay, like I guess what I'm trying to say is like, is there a better way to say this? Is there a better way to say this? Essentially, what I'm trying to say is that I'm just sliding this window. So good, there is x0, x1, x2, x dot. That's the sequence that I had, and I also have a different sequence, uh, like going from x0 to y1, y2. So this is the directions, right? Y1, y2, so on. So what I'm trying to tell you is that like you can just slide this window over in a right way. I'm like having difficulties. So this is where like people use this machinery from like something called coupling from the past. The idea is that like I'm trying to suggest that like there is a different tuple. I am struggling with the notation like at this point in time, y top prime. Sorry? Yeah.
X naught would be the same for computer.
X naught will do the same. Well, actually, you can claim something much better. So let me erase this once more. I'm sorry. I'll call this time tau 0. The claim is that this distribution and the stopping time is tau 1, that these two distributions are exactly identical. These two distributions are exactly identical. No matter whether you want to like start this window at x0 or whether you want to slide it 1 over and start it at x1. So remember, x0 is stationary. So marginally x1 is also stationary. Just one moment. X0 is stationary, marginally x1 is also stationary. So the idea is that like this entire process is frozen at pi cross UST. This entire process is frozen at pi cross UST. The thing that I have not been able to explain well is that how do I slide this window over? Right? That I think I can do, but like I will need more time. Right? Yes, go ahead, Mabel.
Is proportional to the degree at
Oh, it is, right? So how do you return a uniformly random spanning tree? Is that the question?
So then the degree of x1 and degree of x1 should be the same. Only then
No. Remember, marginally, x0 and x1, they are both copies from stationary distribution. x0, x1 का distribution एक है. Both of them come from pi. Okay? Both of them come from pi. Of course, there is an overlap in these windows. दोनों windows में कुछ overlap है. So now we are good. So like I'm kind of struggling in how to like motivate how the window is how the sliding process takes place. But yeah. So if you look at x0 and x1 together, I agree. But if you look at x0 and x1 separately, x0 is a legitimate copy from uniform distribution. ठीक है? अब मैंने x1 separate दूसरे experiment में पैदा किया, right? I mean I like had some different x0, ended with a different x1. So the distributions of x0 and x1, they are going to be exactly equal, pi. Yeah. But like I'm struggling with my notation. I tried my best to avoid negative indices, and that's why I'm struggling. I think I should have used negative indices. So sorry. Anyway, this is the claim you will show. This is the claim that you will show. But in order to show this claim, you have to do a bunch of other things. You have to show that both of these things are equal to an intermediate thing. I have not written the intermediate thing. Two distributions are equal. That's the claim. Two distributions are exactly equal.
Here you started with some x naught, you went x1 to x star. There what are you doing?
तो like देखो यहाँ पे मैंने Aldrich Broder process चालू किया. It starts at x0. The cover time was tau 0. So after tau 0 time, I look at the collection of random variables and I look at the distribution mu av. And the claim is कि अब इसके बाद I drop x0 from this window. I start the window at x1. I look at the next cover time. The next cover time happens at time tau 1. Okay. So the claim is distributions are the same. Distributions are exactly the same. The two of them are equal to one common thing, and since I was trying my best to avoid negative indices or like what is called coupling from the past, I was trying to avoid it. I think that I rubbed myself in some tangles that I have not been able to resolve as well as I would have liked to. So this is, yeah, given the transition probabilities, x1 determines the case.
transition from the pair, start index and the tree to another start index of a tree can only happen.
Okay, like guys, let's do one thing. Let's disband. Okay, and we'll continue this outside.